Okay, we're going to go back to limits here temporarily, and in 4.4 we're going to talk about what's called L'Hopital's rule. So here's what L'Hopital's rule says. Let f and g be differentiable and g prime of x not equal to 0. Okay, if the limit as x approaches a of f of x is 0, and the limit as x approaches a of g of x is 0, or the limit as x approaches a of f of x equal plus or minus infinity, and the limit as x approaches a of g of x is plus or minus infinity, then the limit as x approaches a of f of x over g of x would be equal to the limit as x approaches a of f prime of x over g prime of x. Okay. Now, in order to use L'Hopital's rule, the limit has to be in what's called indeterminate form. Indeterminate form means that you're in the form 0 over 0, or infinity over infinity. Okay? Now, when you use L'Hopital's rule, you're just going to simply differentiate the numerator and differentiate the denominator. Okay? We do not use the quotient rule. Okay? There's derivatives involved, which, by the way, we did a lot with limits back in chapter 2, right? And we didn't see any of this there. Well, that's because in order to use L'Hopital's rule, we have to be familiar with derivatives, and we hadn't talked about the differentiation rules back in chapter 2. Okay, so there was more to know essentially, but we're not using any quotient rule when we apply L'Hopital's rule. Let's take a look at some examples. Suppose we want to find the limit as x approaches 1 of the ln of x over 3x squared minus 4x plus 1. Okay, so if I plug in 1, I would get 0 in the denominator. That's no good. And ln of 1 is 0. Okay, so I'm in indeterminate form, 0 over 0, which means that I can use L'Hopital's rule. Now, this h above the equal sign is notation that you'll see in the book to indicate that at this particular point in the calculation, we're going to use L'Hopital's rule. You can use that if you want or not. It doesn't matter. I'll be using it just to show you, at this particular step, we've used L'Hopital's rule. Okay, so I'm going to use that. I'm going to have the limit as x approaches 1 of the derivative of the top divided by the derivative of the bottom. The derivative up top would be 1 over x. The derivative of the bottom would be 6x minus 4. And if you flip the denominator and then distribute the x, now plugging 1 into the function is no longer a problem, right? You're going to have 1/2 as the answer. And of course, the goal with limits is to make it so that you can have a direct substitution there. Here's another example. The limit as x approaches infinity of e to the x divided by x squared. Okay, x is growing without a bound, so e to the x and x squared are both going to be growing without a bound. You're going to be in indeterminate form, that is infinity over infinity. And by the way, when I'm in indeterminate form, I don't actually write that down. Like I don't write 0 over 0 or infinity over infinity, okay? That should be just an observation that we'd want to make, and hey, we're in that form so we can use L'Hopital's rule. Of course, division by 0 isn't allowed, right? So I wouldn't actually want to write that down anywhere. Okay, and I'm going to go ahead and use L'Hopital's rule. So you got the limit as x approaches infinity of the derivative of the top is e to the x divided by the derivative of the bottom. That'd be 2x. Now, I am still in indeterminate form, right? X is growing without a bound, so e to the x and 2x would also be growing without a bound. I'm still in the form infinity over infinity. So I can use L'Hopital's rule again. Now, in some of these problems, you'll need to use L'Hopital's rule, several times, okay? So let's go ahead and apply that again. You got the limit as x approaches infinity of the derivative of the top is e to the x, to the derivative of the bottom would be 2. Okay, x is approaching infinity. E to the x times 1/2, that would be approaching infinity also. Okay, so my answer here is infinity. Now, a couple of things. First of all, it is worth noting that when you are working with limits, of course, make sure that your limit notation looks good, like we've been doing all along. The notation is important. Okay, make sure that you're writing the limit notation, that you're removing the limit notation when you actually calculate the limit, just like we were doing in chapter 2. Okay, I will be grading you on that. Now, just an observation here with this last calculation, we got infinity. An exponential function is going to grow faster than any power function. Okay, like if I had these two flipped, if I had the limit as x approaches infinity of x squared over e to the x, the calculation would be very similar. You know, you'd need L'Hopital's rule twice, and you'd have the limit as x approaches infinity of 2 divided by e to the x. Well, the denominator would be growing without a bound as the numerator just sits at 2, so the answer there would be 0. Okay. In general, an exponential is going to grow faster than any power function. Like even if this were x to the 10th, you know, at some point the exponential would take that over and produce bigger output values. In general, that's going to happen. Okay, here's another example. You got the limit as x approaches infinity of the ln of 5x cubed divided by the 5th root of x. Now, there's a couple of different ways that you could handle this one. One option would be to go right to L'Hopital's rule. If we were to do that, and we could, by the way, since x is approaching infinity, both the numerator and the denominator are going to be growing without a bound. Okay, and so that would be fine. The only thing is that when you differentiate the numerator, you'll need a chain rule. But another option would be to simplify first what's inside the limit, and then by using your laws of logarithms. So let me use that approach instead. Okay, I know that I can split a single logarithm if I'm multiplying the inner terms into two logarithms. That would be where the operation would be addition. I also know that powers can come out of logarithms there, right? And now this single fraction can be split into two fractions. I can also split the limit into two limits. 3 is a constant, and I know constants can come out of limits. And now this first one here, the limit as x approaches infinity of the ln of 5 over the 5th root of x. Well, the denominator is going to be growing without a bound as the numerator just sits at the ln of 5. So the y values are going to be getting very minuscule, getting closer and closer to 0. Now on this second limit, I would be in indeterminate form. Okay, so I can use L'Hopital's rule on this second limit here, and that's what I've done in the next line. You got 3 times the limit as x approaches infinity of the derivative of the top, that's the ln of, that's 1 over x, divided by the derivative of the bottom, that'd be 1/5 x to the negative 4/5. 1/5 x to the negative 4/5, that'd be the same as 1 over 5x to the 4/5. And if you flip that, you would have 5x to the 4/5 divided by x. Keep the base and subtract the powers. That'd be 5x to the negative 1/5, or 5 over x to the 1/5. And x is approaching infinity, right? So the denominator is going to be growing without a bound as the numerator just sits at 5. And that limit, therefore, would be 0. 0 times any number is 0, so the answer there is 0. Okay, here's another one. The limit as x approaches 0 of tangent x minus x over x cubed. Well, I can't plug in 0, right? But I'm also going to get 0 in the numerator. Tangent of 0 is 0. And so we're in indeterminate form, 0 over 0. So I'm going to go ahead and apply L'Hopital's rule to begin. And you got the limit as x approaches 0 of the derivative of the top divided by the derivative of the bottom. The derivative of tan x is secant squared x, and then minus the derivative of x is 1, divided by the derivative of x cubed is 3x squared. Okay, and now I still can't plug 0 in because it can't divide by 0. But secant of 0 would be 1, because cosine of 0 is 1, right? Secant of 0 is the same as 1 over cosine of 0. 1 over 1 is 1. 1 minus 1 is 0. So I'm in indeterminate form still, 0 over 0. Let's go ahead and use L'Hopital's rule again. So you got the limit as x approaches 0 of the derivative of the top. That's going to be a chain rule. You're going to have 2 secant x times the derivative of secant x is secant x tangent x. Derivative constant is 0. Okay, and the derivative of the bottom then would be 6x. And I'm still going to be in indeterminate form, right? Because if I plug 0 in, tangent of 0 is 0. Can't divide by 0, so I'm still in 0 over 0 form, right? Let's use L'Hopital's rule one more time. So you got the limit as x approaches 0 of the derivative of the bottom would be 6, and so now there's no longer an issue with division by 0. In the numerator, I'm going to need the product rule, and within the product rule, I'm going to be using the chain rule. Okay, so let's let 2 secant squared x be the first term. We're going to have the first, which is 2 secant squared x times the derivative of the second. Derivative of tan x is secant squared x. That'll give us 2 secant to the 2 secant of x to the 4th power. And then plus the second is tangent x times the derivative of the first. Derivative of 2 secant squared x, that'd be a chain rule. You're going to have 4 times secant x times the derivative of secant x is secant x tangent x. And so that gives us 4 secant squared x tangent squared x. Now I can plug in 0. Okay, so I'm going to have, let's see, tangent of 0 is 0. That's going to knock out this part. Secant of 0 is 1. So you end up getting 2 over 6, or 1/3 would be the answer there. By the way, sometimes when working with limits, L'Hopital's rule is your only option. Okay, here would be a situation, you know, where it's our only option. Okay, so it's a pretty handy thing to know. Here's another example. The limit as t approaches 0 of 1 minus cosine of 4t divided by 1 plus t minus e to the t. This would be an indeterminate form. Cosine of 0 is 1, and anything to the 0 power is 1, right? So you're going to have in the denominator 1 minus 1 is 0, plus 0 is 0, 1 minus 1 is 0 in the numerator. Okay, and so I can use L'Hopital's rule. We're going to have the limit as t approaches 0 of the derivative of the top. That's going to be a chain rule. You're going to have sine of 4t times the derivative of 4t is 4, divided by the derivative of the denominator would be 0 plus 1 minus e to the t. Okay, and we would still be in indeterminate form. Sine of 0 is 0, e to the 0 is 1. 1 minus 1 is 0 there. And so let's go ahead and use L'Hopital's rule again. Okay, we're going to have the limit as t approaches 0 of the derivative of the top. That's going to be a chain rule. You're going to have 4 times cosine of 4t times the derivative of 4t is 4. That's going to be 16 cosine 4t divided by the derivative of the bottom would be negative e to the t. And now I can plug in 0. There's no problem with that. You're going to have cosine of 0 is 1, right? So 16 divided by negative 1 would be negative 16 is the answer there. Okay, and that'd be another situation where L'Hopital's rule would be your only option. Here's another one. Okay, the limit as theta approaches pi over 2 of 1 minus sine theta over cosecant theta. Well, let's see, cosecant of pi over 2 is 1, because sine of pi over 2 is 1. Cosecant of pi over 2 would be 1 over sine of pi over 2, or 1 over 1 is 1. Okay, and you would get 0 in the numerator. 0 over 1 is 0. Okay, now the point of this is to say you don't want to blindly use L'Hopital's rule. Okay, some students will want to do that. Like, this is a handy method to know, but the only time that you can use L'Hopital's rule is if you're in indeterminate form. If you're not in either one of these two forms here, you cannot use L'Hopital's rule. Okay, so don't get carried away with it. You know, some students want to use L'Hopital's rule for every single limit problem. You can't do that. Okay, don't use L'Hopital's rule without thinking first. Here's another example. Okay, how about the limit as x approaches 0 of hyperbolic sine x minus x over x cubed. Well, we know there's a problem with division by 0. We can easily see that. Hyperbolic sine of 0, what is that? Well, we talked about the hyperbolic functions back in section 3.11. Hyperbolic sine of x is e to the x minus e to the negative x over 2. So if I were to plug in 0, e to the 0 is 1. You're going to have 1 minus 1 is 0, divided by 2 is 0. Hyperbolic sine of 0 is 0. Okay, so we are going to get 0 in the numerator. We are in indeterminate form with this, so we'd want to begin by using L'Hopital's rule. We're going to have the limit as x approaches 0 of the derivative of the top divided by the derivative of the bottom. The derivative of hyperbolic sine x is hyperbolic cosine x, and then minus the derivative of x is 1, divided by the derivative of x cubed would be 3x squared. And we're still going to be in indeterminate form here because of course there's a problem with division by 0, but hyperbolic cosine of x is e to the x plus e to the negative x over 2. Now if you plug in 0 there, you're going to have 1 plus 1 is 2, 2 over 2 is 1, minus 1 is 0. Okay, so we are still in indeterminate form, 0 over 0. So let's go ahead and use L'Hopital's rule again. We've got the limit as x approaches 0 of the derivative of the top. Derivative of hyperbolic cosine x is hyperbolic sine x, divided by the derivative of the bottom would be 6x. Hyperbolic sine of 0 is 0, so we are still in indeterminate form. Let's go ahead and use L'Hopital's rule one more time here. You got the limit as x approaches 0 of the derivative of the top, that'd be hyperbolic cosine of x, divided by the derivative of 6x is 6. Okay, so division by 0 is no longer a problem. At this point, you can plug in 0. Hyperbolic cosine of 0 is 1, and so 1/6 then would be my answer there. Of course, make sure that you know your rules for differentiation, okay, the things that we talked about in Chapter 3. Here's another one. How about the limit as t approaches 0 of 8 to the t minus 5 to the t over t? Anything to the 0 power is 1, right? So 1 minus 1 is 0. You're in indeterminate form here. Now, the derivative of a to the x is a to the x times the ln of a. We looked at that in section 3.4. So the derivative of 8 to the t, that'd be 8 to the t times the ln of 8. Derivative of 5 to the t would be 5 to the t times the ln of 5. Derivative of t is 1. Okay, and so now I can plug 0 into the expression there. Remove the limit notation. You're going to have ln 8 minus ln 5, which as a single logarithm would be ln of 8/5. And of course, give the exact values. That's what I'm doing on all of these problems here. I want exact answers. That's how the book will want it also. Obviously, no tables, okay, right? Because that's you're estimating a limit. We don't want to be guessing the answers. We want to know for sure what the answer is, right? So here's why don't we just do one more here in this video? The limit as x approaches 0 of x divided by tangent inverse of 4x. Okay, so now I guess I'm just wanting to have you guys make sure that you know your differentiation rules, right? We get 0 in the numerator. Tangent inverse of 0 is 0 because tangent of 0 is 0. So I'm in indeterminate form. Okay, I'm going to have the limit as x approaches 0 of derivative top is 1. The derivative of tangent inverse of x is 1 divided by x squared plus 1. Now I don't have tangent inverse of x, I've got tangent inverse of 4x. So this would be a chain rule in the denominator. Where I see x, I'm going to write 4x, but then I got to complete the chain rule by taking the derivative of 4x. Derivative of 4x is 4. And if you flip the denominator there, here's the next line. Now you can plug 0 in for x and lose the limit notation. And it looks like 1/4 is the answer on that one.